Welcome back for lesson 3.2. We're now going to dive into more particular items in probability with independent and mutually exclusive events. So we're going to go through a few definitions and then jump into some examples. Two events A and B are independent if the knowledge that one occurred does not affect the chance the other occurs. And the way we sample has something to do with this. So, sampling may be done with replacement or without replacement. So let's look at what those mean. With replacement is if each member of a population is replaced after it is picked, then that member has the possibility of being chosen more than once. When sampling is done with replacement, then events are considered to be independent, meaning the result of the first pick will not change the probabilities for the second pick. Without replacement is when sampling is done without replacement, each member of a population may be chosen only once. In this case, the probabilities for the second pick are affected by the result of the first pick. The events are considered to be dependent. If it is not known whether A and B are independent or dependent, assume they are dependent until you can show otherwise. So let's look at the examples here. You have a fair, well-shuffled deck of cards, 52 cards. It consists of 4 suits. So the suits we have are spades, clubs, diamonds, and hearts. There are 13 cards in each suit, consisting of 1 through 10, a jack, a queen, a king of that suit. So sampling with replacement, an example would be, suppose you pick 3 cards with replacement. The first card you pick out of the 52 cards is the queen of spades. You put this card back, reshuffle the cards, and pick a second card from the 52 card deck. It is the 10 of clubs. You put this card back, reshuffle the cards, and pick a third card from the 52 card deck. This time the card is the queen of spades again. Your picks are queen of spades, 10 of clubs, queen of spades. You have picked the queen of spades twice. You pick each card from the 52 card deck. Okay. So, without replacement. So suppose this time you pick 3 cards without replacement. The first card you pick out of the 52 cards is the king of hearts. You put this card aside and pick the second card from the 51 remaining cards in the deck. It is the 3 of diamonds. You put this card aside and pick the third card from the remaining 50 cards in the deck. The third card is the jack of spades. Your picks are the king of hearts, the 3 of diamonds, and the jack of spades. Because you have picked the cards without replacement, you can pick the same card twice. You cannot pick the same card twice. And that's why there were 52 cards possible, then 51 cards possible, then 50 cards possible. So let's look at a few examples. Let's say you have a fair, well-shuffled deck of 52 cards. We have the same situation as before. 3 cards are picked at random. Suppose you know that the picked cards are queen of spades, king of hearts, and queen of spades. Can you decide if the sampling was with or without replacement? Well, noticing that we chose the queen of spades twice tells me that it was with replacement. Because the queen of spades was chosen 2 times. If it wasn't replaced, then we wouldn't have been able to choose the queen of spades twice. Suppose you know that the picked cards are queen of spades, king of hearts, and jack of spades. Can you decide if the sampling was with or without replacement? And we can't tell. It is possible for both. Because even though one of the cards wasn't chosen twice, doesn't mean that we didn't replace them. It's just we don't know if they were replaced or not. So next we have a fair, well-shuffled deck of 52 cards, just like we had before. All the same situation. Suppose that you sample 4 cards without replacement. Which of the following outcomes are possible? So without replacement. a queen of spades, a one of diamonds, a one of clubs, a queen of diamonds. Okay. A king of hearts, a seven of diamonds, a six of diamonds, a king of hearts. So if it was without replacement, we couldn't have the king of hearts twice. So that one is out. A queen of spades, a seven of diamonds, a six of diamonds, and a king of spades. So both A and C are possible. Answer the same question with replacement. So with replacement, they would all be possible. Next, we're going to look at a new definition called mutually exclusive events. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes, and P, the probability of A and B must equal 0. Let's say we flip two fair coins. This is an experiment. So the sample space would be, we could get heads on both. We could get heads on the first, tails on the second, or tails on the first, heads on the second, or we could get tails on both. The outcomes are HH, HT, TH, and TT. The outcomes HT and TH are different. The HT means that the first coin showed heads and the second coin showed tails. Okay. So let A be the event of getting at most one tail. At most one tail means 0 or 1. Then A can be written as 0 or 1 tail. So these three outcomes would suffice for that. Let B be the event of getting all tails. B can be written as T, T, T. That's the only option there. B is the complement of A. So B equals A prime. And so we also know that the probability of A and the probability of A prime, or the complement of A, equals 1. And we can show that here that the probability of A is 3 out of the 4 outcomes, and probability of B is 1 out of the 4 outcomes. It says, let C be the event of getting all heads. That would be HH. Since B is tails, tails, the probability of B and C are equal to 0. B and C are mutually exclusive. You cannot get all heads and all tails at the same time. Now, let D be the event of getting more than one tail. So the only way to get more than one tail is both tails, which would be 1/4. Let E be the event of getting a head on the first roll. This implies you get either a head or a tail on the second roll. So you could have a head on the first with a tail on the second, or a head on both. That probability is 2 out of the 4 outcomes. Find the probability of getting at least one, so 1 or 2 tail in 2 flips. Let F be the event of getting at least 1 tail in 2 flips. So we could have heads on the first, tails on the second. So at least 1 head. Tails on the first or heads on the second. I'm sorry, at least 1 tail is what we're looking at. And then, or we could get tails on both. And the probability of F, the event of getting at least 1 tail, is equal to 3/4. So let's try a couple on our own. We're going to draw 2 cards from a standard 52 card deck with replacement. Find the probability of getting at least 1 black card. Okay, so at least 1 black card. So we could get a black card on the 2 cards, right? Could be a black and no black. We could get no black on the first one and then a black on the second, right? Or we could get black and black. The other option would be no black and no black on the 2 cards, and that's not that option. So 3/4 of the time we're going to get black on at least one of the cards. Okay. The next one says, a box has 2 balls, one white and one red. We select one ball, put it back in the box, and select a second ball, this time with replacement. Find the probability of the following events. Let F be the event of getting the white ball twice. So the white ball twice would be the probability of white, white. So that would be 1/2 and 1/2. So 1/4 of the time. Because if we're going to select 2 balls, we could have in our sample space, we could have white, white, we could have white, red, we could have red, white, or we could have red, red. Let G be the event of getting 2 balls of different colors. So the probability of different colors, the probability of different. So different colors, there's 2 times, when red and white, or red, white and red, or red and white. So 2/4. Let H be the event of getting white on the first pick. So that would be white, white, or white, red. 2/4. Are F and G mutually exclusive? Can we have white, white, and different at the same time? No, we cannot. So yes, they are mutually exclusive. Yes, they are mutually exclusive. We cannot have both white and yet different, and yet both different at the same time. Are G and H mutually exclusive? So can we have different at the same time and get white on the first pick? No, because we could have white and red. That would be white on the first pick, which is H, and different colors, which is G. Okay. So the last big problem for us, use the following information to answer the next 7 exercises. An article in the New England Journal of Medicine reported about a study of smokers in California and Hawaii. In one part of the report, the self-reported ethnicity and then smoking levels per day were given. So they decided what their ethnicity was, so Latino, and their level of smoking must be 1 to 10 cigarettes per day. So there were 12,831 people that identified as Latino, and they smoked 1 to 10 cigarettes per day. So the first thing we have to do is find the totals for each of these. Okay, so we are going to go to Desmos to do that. I'm going to show you how I did this in Desmos. And if we add our first column of the African Americans, we get 18,830 The Native Americans are 8,014. The Latinos are 19,969. The Japanese Americans are 26,078. And the white, identified as white, was 27,559. And then we also have to add the rows. So those were the columns by ethnicity. And now we're going to do the rows, which is your level of smoking. And I'm just going to put a note in here. This is better. Okay, so the level of smoking is down below here. So we have 41,490. And then go ahead and fill these in. It would be good to take a minute and to do them on your own to verify. So then I added all of the column totals and the row totals, and I verified that altogether there were 100,450 people that responded to the survey. So let's go ahead and answer our questions here. Back to the paper, and you can verify that you have what I have on your paper. So here are the totals. So this is how they answered as far as their ethnicity, and then the row totals are how they answered their level of smoking. One person from the study is randomly selected. Find the probability that person smoked 11 to 20 cigarettes per day. So that's all we want to know is 11 to 20, and that would be 35,065 divided by the 100,450. And if we divided that, we would get, and you could write that as a percentage if you wanted, 34.9%. Find the probability that the person was Latino. So that would be this column here, Latino. So 19,969 out of the 100,450. I'm going to round that to 19.9%. And then C says, in other words, explain what it means to pick one person from the study who is Japanese American and smokes 21 to 30 cigarettes per day. Also find the probability. So they have to do both. So that would be Japanese American. So right here, Japanese American. And they smoke 21 to 30. So they're in both categories. So it means that it's this cell here, 4,715. So let's just highlight that. So they are Japanese American and they smoke 21 to 30 cigarettes per day. So it's this group of people right there in particular. So 4,715 out of the 100,450 is, if you turn that into a decimal, or a percentage, it's 4.69%. Pretty low. But it does look like the group that smokes the most cigarettes per day are the white. They were the largest number of people that responded to the survey. So Okay. D says, in words, explain what it means to pick one person from the study who is Japanese American or smokes 21 to 30 cigarettes per day. Also, find the probability. So, or means they could be in both. They don't have to be in both, but they could be in either or. So because they overlap, we have to subtract, let's just write that off to the side, the overlap. Okay, so it's going to be the probability that they're Japanese American plus the probability of 21 to 30. And then we're going to subtract their overlap. So in that case, it would be 26,078 is the number of Japanese American plus the 15,273 that smoked 21 to 30, subtracting the overlap of the 4,750. So we're basically subtracting the and. And so this comes out to be minus the 4,715. This is the 36,636 divided by the 100,450 is 36.5%. So remember, if there is some overlap, if they say or, there's a possibility that they could be in both. And that is the case. The or is, we want to know the Japanese American or they smoke 21 to 30 cigarettes per day. And if we include this 4,015 twice, we can't count me twice. So we have to subtract any overlap. So that concludes lesson 3.2. And catch me back, ask me if you have any questions, send me messages, meet me on the Zoom. Otherwise, catch me back for lesson 3.3.